0 but less than 1. So of course here my alpha was like this. Okay, so if my alpha is like between of course greater than equals to, you can say 0 to 1, then Lipschitz map is called contraction map. Then Lipschitz map for a contraction map. It means that image is always less than equals to 1. So again you can see here that is d of tx ty over d of xy is less than equals to alpha, but alpha is 1. So means ratio of d of tx over ty over d of xy is always strictly less than 1. This is it means that these images in every step they are basically going closer to each other in every step. Okay, so this is the definition of the contraction, or sometimes people use the word contractive map also. Third one, if I consider alpha equals to 1, then map defined here means Lipschitz map is called the non-expansive map. So here, then this definition t of tx dy becomes less than equals to d of xy. Of course, for all xy, then such map is called mappings are called are known as or are called non-expansive. Okay, so here we have just we can consider some examples, very simple example in the favor of these definitions. So just very simple examples. Of course, maybe I can read one more definition here. Fourth one, definition or is a remark. A mapping T is said to be contracting, or sometimes authors call the strict contraction. Okay, so I will use a word strict contraction. If d of tx ty is strictly less than d of xy for all distinct xy in x, because xy cannot be equals, because when x and y are equal, then of course it is 0, and this is always non-negative because bt function is a non-negative function. Then of course anything cannot be, means d cannot be negative from this part. So this is called the strict contraction, but some author call it a contractive map also. Okay, so let us see example. So of course this another just simple comparison between these maps, like this contraction always imply the this non-expansive map, and this contraction always also imply strict contraction because alpha is greater than equal to. So this is the one remark is here. D of, so suppose this is my contraction map, and alpha is my strictly less than 1. That's why this quantity is also strictly less than 1. But of course for all distinct. So that's why contraction imply strict contraction. Okay. So let us say some examples and later on more observations on these maps. So first of all, and of course contraction, strict contraction, these are always implied Lipschitz map. Because all are this contraction map, strict contraction, and non-extensive map, all are the basically subclasses of the Lipschitz map. So Lipschitz map is a very bigger class because in the definition of the Lipschitz map, by alpha is any non-negative, any positive number. So example is here is a simple one. If I define T from R to R, so R is my metric space with the usual metric space, so I can say T is a map from RU to RU, means with the usual metric, and defined by T of x. So if I define Tx equals to 4x, so of course this is a Lipschitz map with Lipschitz constant 4, because if you consider this mod of what the metric here mod. So Tx minus Ty is equals to mod of 4x minus 4y equals to 4 times mod of x minus y. So d of Tx minus Ty is basically 4 times d of xy. So this is basically my Lipschitzian map. Sometimes we call it a Lipschitzian or Lipschitz map with the Lipschitz constant 4. Of course, but this is not a non-expansive map, or you can say contraction map or strict contraction. Next example, if I I'm going to consider the previous examples like this. Tx equals to xy. I already considered this example. So again, we can see here Tx minus Ty is equals to mod of xy2 minus yy2. So this is half of mod of x minus y. So of course, this is alpha times mod of x minus y. So where alpha is which is strictly less than. Here alpha was my 4. So of course this is an example of a contraction map. So this implies that T is a contraction. Some more example like translation or identity map. If you define T of x equals to x plus maybe you can say a, where a is non-zero, then of course you can check easily mod of Tx minus Ty equals to just mod of x minus y. So of course my here alpha is 1. So this is basically my non-expansive method, and of course alpha is 1. So automatically this is a Lipschitz map or Lipschitz map, of course, for all x and y. Okay. Now, just I am going to construct, and of course, this is also an example of a strict contraction because alpha is half, so that's why this is inequality. It means that this is also strictly less than y mod of x minus y for all distinct. Because every contraction is a strict contraction for the distinct element, so that's why this is also an example of a strict contraction. But converse is not true. Means we have contraction, then imply strict contraction, then imply the Lipschitz class, but converse is not true in this way. And same thing for the non-expansive and strict contraction and then Lipschitz class. But converse is not true. So we have some counter examples. So let us see this example. So basically, this is one of the exercise from the book of the this function answered by Krasik. So on page number 304, this is exercise number 4. So my x is set, and of course with respect, so this is a subset of R. So here we can consider the user metric space and define map T, of course from x to x, by this rule T of x equals to x plus 1 over x, of course for all x. So claim is that mod of, because my metric is here usual metric, so that's why mod of tx minus ty is strictly less than mod of x minus y for all distinct x and y. So you can say my claim is that T is a strict contraction. So this is a just a simple exercise, so you can do by yourself. If any doubt, then we can discuss in the tutorial class. So this is one example. Okay, another example. Just not example again. This is exercise. Exercise number 2 on page 303. So this exercise, my again x is my same set. Subset of real numbers, and T is in my map from x to x, of course with the usual metric. So usual metric is understood here, and again define, this is modification of this example, defined by this rule T of x equals to xy2 plus 1 upon x for all x in x. So my claim is here T is a contraction map for some fixed alpha in open interval 0 to 1. Because for 0 it's not a means for if you consider alpha is a 0, then it's a very trivial case. So claim is that T is a contraction. Contraction of X, that is mod of Tx minus Ty is less than or equal to alpha times mod of X minus Y for some alpha in open interval 0 to 1. Because when we take alpha is 0, then everything is negative. So only sometimes we consider this should be in the open interval. So this is more appropriate as compared to the semi-closed open interval 0 1 from the 0 side. So if with that, just so question is that here find this alpha is what is the value of alpha is here. So just you can start with the this thing and then you can go. So this is just for your exercise and this. So these two exercise for your assignment. This is your assignment. And this is also for your assignment. Okay. Another important thing is here. These mappings, or sometimes we call it say operator. These are the non-linear operator or non-linear map. Because for the linear map, existence of the fixed point is always trivial. Means that part, first part of the existence of fixed point is always trivial. So why is trivial? So this is my maybe question or simple exercise. If T is a linear map, then existence of fixed point is trivial. In case of linear operator or linear map, so you know what I mean by the linear operator, linear transformation, or you can say. So existence of fixed point is trivial. So that problem is not interesting. So that's why we always, in this course, we will consider the non-linear operator or non-linear maps. That's why this course is a non-linear functional analysis. So of course, you will get the answer of this problem. Answer is very trivial. Okay, so existence part is very trivial here. Another thing for the maybe some more examples. So in the previous examples, I considered some mapping like Tx equals to x square, means quadratic equation, or you can say it's a polynomial, like we can consider simply Tx equals to x. So there is a polynomial of degree 2, x square minus x equals to 0. Similarly, we can consider Tx equals to x cube. So this is again considered as a polynomial of degree 3. So it has the 3 roots. That's why it has a 3 fixed point. And similarly, we can consider the polynomial of degree n. So of course, from there that has the maximum n roots. So that's why we can have the idea of the maximum n fixed point of the given map. So these are the basically polynomials. So my question is that find out those examples which has the basically 3 fixed point or maybe 100 fixed point, but those are not the polynomial type functions. It may be simply